Grid weak versus strong. The terms weak or strong are often used to describe the grid, but they are rarely explained. A strong grid, from a load perspective, means a connection with low Thevenin impedance or a direct link to the sources feeding it. The Thevenin impedance at a load represents its connection to all generators. Conceptually, it is like a representative fictional generator feeding the load through an impedance that represents all transmission paths. If the Thevenin impedance is low or the load is close to generation, the connection to the grid is strong. A strong connection provides steady voltage that doesn't vary much with load, power factor, or reactive capacitive current. The generators can be viewed as voltage sources, and the closer the load is to the source, the stronger the voltage is maintained. Conversely, a weak grid's voltage will tend to fluctuate with the load. Another characteristic of a strong grid is its ability to provide significant phase fault current, while a weak grid cannot refer to phase current, not all fault current, because a strong connection has low positive sequence impedance. Normal power flows are balanced, and a strong connection has low Thevenin positive sequence impedance. The grid's passive elements, like transmission lines and transformers, keep the negative sequence impedance the same as the positive sequence. Phase faults involve positive and/or negative sequence impedances. A strong grid connection by default means the phase faults will tend to be high. Ground faults can be impacted by positive and negative sequence impedances but are often limited by the Thevenin zero sequence or ground impedance. Few spots on the grid have ground sources delta Y or zigzag transformer connections on a solidly grounded grid. On high impedance or ungrounded systems, the grounding impedance, or lack thereof, completely limits ground fault current. Relaying engineers often refer to weak and strong connections based on available phase fault current. Load step-up transformers are usually specified with impedance to reduce available phase fault current at the expense of voltage regulation. Transmission and distribution planning engineers are more concerned with positive sequence impedance when describing a system as weak or strong because they are more concerned with feeding load than faults. Grounding's impact on ground fault current is becoming clouded as inverter-based sources need to be programmed to supply negative sequence current so that ground and unbalanced faults can be fed fault current. If the inverter is not programmed to supply, or is limited in supplying, negative sequence current, the fault current could be restricted by inverter-based generation, not by how the system is grounded. This is very different from synchronous generation. Strong grid systems invest heavily in the latest technology and materials for building power plants, transmission lines, substations, and distribution systems. They use advanced high-voltage lines such as HVDC for long-distance transmission, which significantly reduces losses and can carry large loads. Strong grids have well-funded and organized maintenance schedules, preventing failures through regular checks and preemptive repairs. Weak grids often rely on older, inefficient, and outdated infrastructure, which leads to high transmission losses and frequent equipment failures. Weak grids may use low-voltage lines, which are prone to losses and overloads, particularly when the demand spikes. Repairs are often done only after failures occur, resulting in prolonged downtimes and inconsistent power supply. Strong grids use sophisticated systems like SCADA, Energy Management Systems (EMS), and Distribution Management Systems (DMS) to monitor and regulate voltage and frequency in real time. They use devices such as transformers with tap changers and capacitor banks that automatically adjust voltage levels to maintain stability. They can handle fluctuations in demand and supply due to high penetration of renewables and distributed generation. Weak grids often experience significant voltage swings, leading to equipment damage, inefficient energy use, and even power outages. Weak grids may not have the technology or resources to continuously monitor and control voltage and frequency. Manual interventions or outdated relay systems are more common, increasing the risk of instability. Due to limited infrastructure and fewer technologies in place, weak grids struggle to cope with variations in demand, renewable energy integration, or even minor faults. Strong grids have multiple, interconnected pathways for electricity transmission and distribution, meaning that if one line or substation fails, power can still flow through other routes. This reduces the likelihood of widespread outages. These systems are often designed with an N-1 principle in mind, meaning that the grid can still function even if one key component, e.g., a generator or transmission line, goes offline. Strong grids experience fewer interruptions due to redundancy, advanced maintenance, and reliable equipment. In weak grids, a single fault in the transmission or distribution system can often lead to cascading failures and large-scale blackouts because there is no alternative route for the power. Weak grids usually lack the capacity to continue operating after losing a critical component, leading to outages that affect entire regions. Due to lack of redundancy, weak grids have a higher mean time to repair (MTTR), resulting in frequent, prolonged outages. Strong grids are often transitioning toward or have implemented smart grids, or automated systems, real-time data, and advanced communication networks such as the Internet of Things are used to optimize performance. Technologies like automated feeder switches, intelligent fault detection systems, and grid-tied energy storage allow the grid to respond instantly to changes or faults. Strong grids incorporate DSM technologies that allow for real-time response to changing demand, shifting consumption away from peak times to reduce strain on the grid. Weak grids often rely on manual processes for many aspects of grid operation, including fault detection, load balancing, and maintenance, which increases response times and the likelihood of human error. Without technologies like smart meters or SCADA, weak grids have little visibility into what is happening at different points in the system, making it difficult to optimize performance or prevent issues. Weak grids lack the infrastructure for effective demand-side management, leading to frequent overloads during peak periods, as they cannot shift or reduce demand dynamically. Strong grids incorporate a wide range of energy sources, including fossil fuels, nuclear, hydro, wind, solar, and geothermal. This diversification provides energy security and reduces dependency on a single source. Strong grids have the ability to integrate large amounts of renewable energy while maintaining stability, thanks to grid upgrades, storage technologies, and efficient grid management practices. Strong grids tend to have robust domestic energy production and, when necessary, trade energy with neighboring countries to secure supply in times of shortage. Weak grids often rely heavily on a single or few energy sources, such as coal or hydropower. A drought, fuel shortage, or technical failure can cause severe power shortages. Weak grids lack the flexibility to incorporate significant amounts of renewable energy, as they often don't have the technology or infrastructure to manage intermittent supply like wind and solar. Weak grids may rely heavily on energy imports, making them vulnerable to geopolitical tensions, price fluctuations, and supply interruptions. Strong grids use highly responsive protection systems, such as differential protection, distance protection, and automatic wreck losing systems, to isolate faults quickly and restore service. Strong grids are designed to handle disturbances such as short circuits or equipment failures without significant impact on grid stability. Strong grids employ real-time fault location technologies, reducing repair times and minimizing the impact of outages. Weak grids may only have rudimentary protection systems that are slow to detect and respond to faults, resulting in more widespread outages. A single fault can destabilize a weak grid due to insufficient fault isolation and recovery mechanisms. In weak grids, fault detection is often manual and slow, leading to extended outages while crews work to locate and repair the issue. Strong grids are designed with climate resilience in mind, with transmission lines, substations, and generation facilities engineered to withstand natural disasters such as hurricanes, floods, earthquakes, and extreme temperatures. After a natural disaster, strong grids have emergency protocols and resources including mobile generators and fast repair teams to restore service quickly. Weak grids are often poorly equipped to handle natural disasters, with aging infrastructure more likely to fail under extreme conditions. Recovery from natural disasters can take